Hello and welcome everyone. In this video, we will look at another implicit scheme which is known as Crank-Nicolson method. And unlike the previous two methods that we discussed, it is second order accurate in both time and space. We start by taking the forward difference at the nth time step, and at the n plus 1 time step, we take the backward difference instead. And then by averaging these forward and backward differences results in the equation, we get the Crank-Nicolson method formula for solving PDEs. Alpha here is equal to delta t divided by 2 delta x squared. The stencil in this case comprises of 6 points, and we can also write the equation in the matrix form where A and B are both tridiagonal matrices. For each time step, we can solve this system of equation like in the previous video. We can update our Python code to generate the tridiagonal matrices A and B. Then for each time step, we solve the right hand side to get B and then use that along with A to solve for temperature. Using both delta x and delta t equal to 0.01, we get this solution. When compared with the explicit finite difference method, Crank-Nicolson method is unconditionally stable. It is more accurate, but since we solve the system of equations, it can be numerically intensive for large systems. On the other hand, explicit finite difference is less accurate and can be unstable if time steps are not chosen carefully. The advantage of this approach, however, is that it is easier to implement and is computationally efficient. This concludes our video. I hope you liked it. Please subscribe to my channel and thanks for watching.